All right, here's what we want to do. In this video, we want to investigate the topic of regression analysis. It is the biggest topic we're going to talk about this semester, and I want to go ahead and take a look at what it is, introduce the general idea to you, and then specifically in this section, we're going to take a look at a topic called simple linear regression. So let's get right into it. The idea is there's some variables we want to predict. I'll give you a couple examples. We want to predict the sales price of a house. Now, you know, with the data set you guys are working on this semester, that I'm limiting you to the size and the location of the home and saying those are the variables that I want you to use. Those are the predictors. But there's other variables like the age of the house, the condition of the house, for instance. Does it have a security system? Does it have a pool? All these are decent questions to ask and may affect the sales price. But what we're going to find as the number of variables increases, so does the complexity of the regression modeling that we're going to do. Sometimes these variables are obvious. And what I mean by that, as the size of the home increases, what do you expect is going to happen to the price? Well, of course it's going to go up. You would think that, right? Sometimes the locations are fairly well known. If you say, well, let's compare homes in Tampa versus homes in New York City, I think you're going to agree with me that homes in New York City are probably going to be more expensive. And so we'll have an idea how the location variable is going to affect the price. Other times, however, and age is a good indication, we may not know how the variables will interact or work together. Maybe that's the best way. How age will predict the price. And initially you might say, well, older homes are going to, be less because newer homes, they're newer. They have, won't need a new roof. They won't need new air conditioning. So the newer homes, the younger the age, the more expensive. However, what about historic homes? Don't you think you might get to a place where maybe age, as it gets older, it's a bad thing, but then all of a sudden, as you start getting more historic homes, well, now it becomes more desirable. And so sometimes the relationships are pretty well known or pretty straightforward, and other times they're not. Let me use the other two examples. Price of a used car. Again, model and mileage is what you're using if that happens to be the data set that you're working on this semester. But things like what kind of transmission does it have? Is it automatic or is it a 4-speed or 5-speed? Manual transmission is typically how you would think of that. Is it a convertible? Yes or no? So different variables will affect the year of the car. Probably has an effect. Is year related to mileage? Yeah, probably. But that's what we want to look at. How do these predictors help us to predict the price that we're interested in? The rent of an apartment, size, location, amenities. Does it have a fitness center? Is there a pool there? Does it have trash pickup? Lots of different variables. Some of the predictors are quantitative, some are qualitative. So let's talk specifically about simple linear regression. And so in simple linear regression, we're going to try to model one variable, and we're going to call that variable y, the dependent variable. And for our purposes, the dependent variable is going to be a quantitative variable. Now there is a branch of regression called logistic regression where you can predict a qualitative variable, but for our purposes, we're going to stick with quantitative dependent variables. So we're going to predict a quantitative dependent variable based on other related x's, and the x's typically can be quantitative or qualitative, but however in simple linear regression, and I'll abbreviate that SLR from time to time, we're going to hypothesize a straight line relationship between x and y. And for our purposes in simple linear regression, the x's are going to be quantitative. After we do simple linear regression, I'm going to introduce different types of model terms. We're going to get more complicated. I'm going to allow for qualitative variables and talk about how do we do mathematical models with categories. Well, it's not too hard. We can do that. But we're also going to introduce a couple other ideas as well. An idea of, well, what happens if we don't want a straight line? Could we work with curves? And the answer is sure we can. We can absolutely work with curves. And then there's another idea called interaction. And I'll save that discussion for a model terms video or discussion that we'll need to have. But let's do the simple linear regression first. And when you're talking about straight line relationships, think algebra. Think about the straight line relationship, mx plus b, right? That's what everybody uses. Oh, wait, not everybody. We don't use mx plus b. We use some other symbols, and I'll get to that in a second. As you add variables, as you get more complicated, our mathematical relationships are going to get more challenging as well. So for the near term, we're going to just be working with straight lines. And I guess I should mention, I could talk about straight line relationships between two variables. There's an idea, and we'll talk about it briefly. It's called correlation. Correlation between two variables, between x and y. And we could probably do that in a half-hour discussion. We could probably talk about correlation and talk about the straight line relationship between x and y in about half an hour. I'm not choosing to do that. I'm going to take a bunch of time and go through all the simple linear regression videos and the topics and the ideas. And I'm doing that primarily because I want to use a simple linear regression as a stepping stone to our multiple regression. We're going to see a lot of similarities between simple linear, and multiple regression. And if we can get some of the base knowledge out of the way here with simple linear regression, then we can concentrate on the more complicated parts. The quadratic terms, the interaction terms. What are they? How do I do it? The model building. When we're talking about a simple linear model, there's just one model to consider. All of a sudden, when you start introducing other terms, other variables, now it's like, well, do I want to include those variables? How do I know if I'm doing a straight line or a curve? What the heck is interaction? And so we'll tackle some of those more complicated issues under the umbrella of multiple regression. We're also going to do something called residual analysis, but I'm getting way ahead of myself. Let's take a look at some models. So here's what we're going to do. Let's talk about two types of models. That mx plus b idea, the way that we're going to write it, mx plus b, of course, we're statisticians. We use Greek symbols. There's a better chance to confuse you. Beta naught plus beta 1x. That's the relationship that we're going to start with, and that's called the deterministic model. And that's an exact relationship between x and y. It's exactly the same as mx plus b. We're just using the betas. The two betas, you may remember what the m and the b stood for. Beta naught represents the y-intercept. Beta 1 represents the slope of the line. And so if I draw a little relationship between y and x, what we're saying is if you tell me the value of x, it's going to fall on the value on the line at the value of y. So if x is over here, I'm going to come up and the value of y would be this. Okay, and so let me go one more here. All points must fall on the line. And I guess naively, it's like, yeah, that makes sense. That's a good model. Let's go with that. However, think about it. Are all 2,000 square foot homes the same price? Are all automobiles that have 20,000 miles the same price? No, of course not. Are all apartments that have 800 square foot, do they all fall on the line? No, of course not. And so while the straight line model, the deterministic model, I guess I should say, the exact relationship is a starting point, we quickly realize that, you know what, that's not going to work for us. And so we take this idea and then we add a component to it. And so what we're going to actually use is called the probabilistic model. We take that deterministic part and then we say, yeah, but we have some wiggle room. And that Greek letter there is it looks like an E or a funny E. It's an epsilon, a Greek letter epsilon. You may also write it, I'll come up here out of the way. Sometimes you'll see it drawn this way as well. Okay, it's another way of drawing an epsilon. And what that's saying is that sometimes the points fall around the line. Okay, so let me go on. Another way of writing this equation is this way. We can write the model two ways, and you're going to have to get used to this because we do it a bunch. We can write it in terms of y, and now I'll mention a y as a single value. If I'm talking about the homes, the price of a home has something to do with the size of the home. Okay? The price of the home has something to do with the size of the home. However, let's come over here. When I look at 2,000 square foot homes, maybe this is 2,000, the price of the home doesn't have to fall on the line. It might fall a little bit above. That's a really big point. But there's another 2,000 square foot home that falls right there. Is there a value or a 2,000 square foot home that falls on the line? Sure. But what we see are the points don't necessarily fall on the line. They might, but more often than not, they're going to fall around the line. And so really what we start looking at is, what's the line that fits our data values the best? Okay, now the y is a single value. The e of y, the expected value of y, sometimes it's referred to, that's the average of all y's. Okay, Y is the value of a single one, the price of a home. E of Y is the average of all. And so I'll say the average price of all homes. And now when we talk about regression, we don't just talk about the homes, we talk about specific values of X. So Y is the price of a 2,000 square foot home. E of Y is the average price of all 2,000 square foot homes. Big difference between that. If you're buying or selling houses, you're probably interested in a specific home. When I go to sell my house, I'm going to be interested in the price of my home. Someone that's looking to purchase a home is going to be interested in the area as well. So they will be interested in the price of my home, but they're also going to be interested in the average price of all homes that are that size in that area. And so there's times for both, and we'll see that as we move forward. Right now, I just want to point out that there is a difference between these two symbols. Whenever you see Y, you need to have the epsilon, because what we're going to say is the individual values fall around the line. That's the points you see here. And then the actually averages, or the EOYs, the mean of the Y values, fall on the line. So if I come down here, say to 1,500 square foot homes, that's the average price of all 1,500 square foot. This is the average price of all 2,000s. There's the average price of all 2,500. Here's the 3,000 square foot homes. So the averages fall on the line. The individual values fall around, and ultimately it's a much more realistic relationship between data. Data doesn't have an exact relationship most often. Occasionally you can look at some data sets where it's exactly, there's a mathematical model, for instance, like insurance rates. You put your numbers into a model and you get your insurance rate. And there is an exact relationship because it was set using a mathematical model. Most things have error, a random error component, and so most of the Y values will fall around the line. So this is the model we're going to work with. Yay, epsilon, good times. We'll talk a little bit later on about, well, is there any kind of rules to how the points fall around the line? And the answer is, yeah, there is. And so here's a good example of some diamond prices. There's a data set in the textbook called the diamond data set, and I just plotted, I did a scatter plot. I did the prices versus the carats, and you can see as the size of the diamond increases, as I move from left to right, what are we noticing? Well, the price is increasing too. Anyone who's ever purchased a diamond or thought about purchasing a diamond, you realize that that's the case. Now, you might also see here a couple things. First, if I look from left to right, I don't really see a straight line, do you? If I was going to, I'm drawing with a mouse, so bear with me here. If I was going to try to capture where the data falls, I would probably draw something similar to that, and that's not too terrible. But it looks like an upward facing curve. And so it doesn't look like a linear relationship. And the other thing I'm going to notice here, look at the variation in the data. When you're looking here, there's a very tight grouping of the diamond prices. But as it gets up here, it starts to get wider. And then look up here, it's even wider. And so the variation of the diamond prices seems to be increasing as I move from left to right as well. And these are going to be some things that we talk about because we're going to have certain assumptions. And one of the assumptions is going to be equal variances. We're going to say it a little bit different. But this would be a data set where that assumption is probably violated. But that's what we're looking at. We're looking at relationships between variables. We're going to probably want to look at a curvilinear model between price and size, between price and carat size. And that'll be something we look at in multiple regression, but it is a decent little data set that I can show you. All right, so that's kind of an introduction to what we're attempting to do in simple linear regression. I'm going to do one more piece here. I'm going to take you through the first step. And you're like, steps? What are you talking about? Well, there are 5 steps in a regression analysis, and I'll put them all up here, and then I'll talk about them. There they are. First thing we want to do is hypothesize the model. And that's a simple linear regression model. We've already got that. That's a piece of cake. The second step is to estimate the betas, because remember, our model is going to, what did we say? It's y is equal to beta naught plus beta 1 x plus epsilon. So there's some betas, and the betas are just trying to say, what's the equation? What's the best fitting line to those data points? And we'll talk about that. And I'm actually going to do a separate video for each of these. I guess I should mention here in simple linear regression, this part is really easy because there's just one relationship we're considering. When we move to multiple regression, this thing becomes tough. Hypothesizing different relationships, talking about what we could see, which variables are necessary. Do I need lines? Do we need curves? All those questions I mentioned earlier, and then more. get asked. So that part becomes a lot more challenging when we get to multiple regression. The estimating of the betas, this is a computer thing. We're gonna use the computer. This is the math. Back in the day, back when I was in college, man, that was tough stuff. I took a class called Matrix Algebra that almost made me want to quit. It was terrible. And now I don't have to talk about any of that now. I can look back fondly and laugh. Actually, I can look back not so fondly and laugh and think, gosh, you guys are so lucky to have the computer. It's so easy. I'm going to replace that work with something else. Don't get me wrong. But I don't need you to do the math. I want you to tell me what the betas represent. So we're going to talk about some beta interpretations. And so I'll underline some things as we go through here. And those underlines are going to say, here's some things you're going to need to interpret for me. Before we do any testing or confidence intervals or any of our tools that we've learned so far, we need to make some assumptions for epsilons. A little while ago I said we're going to take a look to see how the values of x or y fall around the line. How those points, are there any assumptions that we need? And we call those assumptions for the epsilon term. And as part of them, we're going to mention the variance and the standard deviation. We're going to need to estimate the standard deviation. Again, the computer will do that for us, but I'm going to put the underlines because you're going to need to interpret a standard deviation. Good news is you know how to do that. Most things fall within 2 standard deviations of the mean. You've used that interpretation before, hopefully correctly, and you're going to see it again. And so there's another assumption there or another interpretation there for you. Test the model to see if it works, and I'm actually going to link these two up here. We have a model, and so when we get to the 4th step here, we're going to talk about what does it mean, test the model. What does that even mean? How do we do that, and how do we accomplish that? It turns out it's going to be a test hypothesis, and then there's going to be a couple other values we talk about. Correlation coefficient's one. There's another one called the coefficient of determination, which we'll talk about in the 4th step. But that's how we're going to evaluate whether the model is useful or not. I should say whether it is statistically useful or not. I link these two up because as I start taking a look at in multiple regression, I'll put a little different color here on it, I think. Let's try that. As we start hypothesizing different models, that's going to be a multiple regression type of thing. Testing the model to see if it works gets a little bit more challenging because we have more than one model to consider. And so we're going to be asking questions like, how do I know which model? How do I know if I need lines or curves? And we're going to get into a topic called model building. And model building is a pretty important topic, and it's one where a lot of times students pick it up pretty quickly, but there's some who are stumbling, who will stumble on it. And I'll try to help you with that, give you lots of examples to work through. So then after we test the model, this is to say, is it statistically useful? Now we're going to use it. We're going to use it for confidence intervals and prediction intervals. For estimation of E of Y, we might want to estimate the average of all 2,000 square foot homes, and we might want to predict the value of a single 2,000 square foot home. So in the test of the model, that's a test hypothesis. You're going to be interpreting a p-value and then some other things that I'll introduce. For the last part, these are confidence intervals. You need to be able to interpret confidence intervals for me, and we're going to be looking at practical interpretations. You're all set up for it. You have the groundwork already laid. Now we're going to be saying things like we are 95% confident the price of a single 2,000 square foot home falls between these two numbers. We are 95% confident the average price of all 2,000 square foot homes falls between these two numbers. And so we're going to be making practical interpretations. So we got a standard deviation, we have a test hypothesis, we got some confidence intervals. These are some things that at this point in the semester you should be starting to feel pretty comfortable with. Oh, don't worry, I'm going to throw you off. I'll give you some other things to think about. Beta interpretations, what the heck is that? Some other assumptions, model building, model terms. So we're going to hit some topics along the way, but let's try to keep the stuff we already know simple. And so that's the approach. Now, what I want to do in this video, I know I'm getting close to 20 minutes here. I want to just talk about hypothesizing the model, and then I'll cut it off. And the way I want to go through this, I'm going to go through these 5 steps with you. The way I want to do it is in the context of an example. And I've been using this example for years and years and years, and it works. We want to predict the firm's sales revenue for next month using the monthly advertising expenditure. And so the dependent variable, the thing we want to predict, is the sales revenue, monthly sales revenue. The independent variable is going to be our monthly advertising expenditure. I didn't put the word monthly in here, but I could have. They're both quantitative. They're the only variables that we're going to be looking at. Are there other things that predict sales revenue? Sure. How about number of salespeople? There's probably a bunch of different things that you could think of that'll predict the sales revenue for a particular month. We're limiting you. I'm limiting you to just one of each because we're doing a simple linear regression. And so the first thing we want to do is hypothesize a straight line relationship between x and y. And really what you realize is in simple linear regression, it doesn't matter what your x and y are. These are always going to be the models. And you can write it either way. Just remember, if you use the y, there better be an epsilon on the end. And if you use an e of y, I don't want to see an epsilon because the y values fall on the line. The e of y values fall off the line. And so that's the first step. Piece of cake. Hypothesize a straight line relationship between x and y. Again, this part gets a little more challenging when we add variables, add different ideas to it in multiple regression. But for now, that's how we do it. mx plus b on steroids with betas. That's what you want to think about. So took a long time, took a little over 20 minutes to get that information to you, but that's the first step of a simple linear regression analysis. We'll come back in the next video and we'll talk about how do we estimate those betas? How's that done? Well, we're not going to do the math. I want you to have a little bit of a foundation for the way that's done. So we'll talk about it in the next video. Until then, so long.